We will map every solution to chapters 1, 2, and 3 of your Statistical Thermodynamics problem set in exactly 6 minutes. This specific set of 25 problems comes from the Middle East Technical University's Physics 430 course. The information density here is going to be high. Keep your finger over the pause button. When a mathematical derivation fills the screen, stop the video and ensure your own notes match the steps. Taking an exam often feels like navigating a maze of variables. By categorizing these problems by their underlying mechanics, we can build a structured roadmap that turns a complex test into a logical checklist. Let's start by looking at Chapter 1. Step 1 is isolating your state variables. For problem 1.1, that means rearranging the van der Waals equation to solve for pressure. From there, problems 1.2 and 1.6 require writing out the total differentials for internal energy, U, and enthalpy, H. This allows you to extract the definitions for heat capacity at a constant volume, CV, and constant pressure, CP. Next, we calculate work. This is a PV diagram showing 3 expansion paths starting from the same initial pressure and volume. Work is the geometric area under these curves. Visually, the flat isobaric path produces the most work, followed by the isothermal path, and then the steep adiabatic path. Problem 1.10 asks you to prove that visual ranking mathematically. When you integrate the isothermal path, you get a natural logarithm. To compare it to the other paths, use a Taylor series expansion of the natural log, resolving it out to the second order of epsilon. Integrating the adiabatic path leaves you with a fractional exponent. To make it match the format of your isothermal answer, apply a binomial expansion. Once both are expanded to order epsilon squared, the math proves the adiabatic work is the smallest of the 3. Problems 1.8, 1.9, and 1.11 apply these concepts to physical systems, like bubbles in an explosive liquid or heating a water tank. Your job is to tally the energy inputs, sum the mechanical work, whether that's mass times gravity times height, or P delta V, and add it to the thermal energy from heat capacity or an electrical resistor. The first law of thermodynamics behaves like a conservation ledger. Once you define the process path, isothermal, isobaric, or adiabatic, the specific mathematical identity required to solve the energy balance becomes fixed. Moving to Chapter 2, there is one mandatory rule. Convert every temperature to absolute Kelvin before starting your calculations. With your temperatures in Kelvin, problem 2.2 is a direct application of the Carnot efficiency formula, 1 minus T cold over T hot. For problem 2.13, you run that same relationship in reverse to calculate the work required for an ideal refrigerator. Problem 2.6 maps a multi-step cycle through 4 distinct states. You are given the high and low temperatures and the initial pressure and volume at state A. To find the limits of the cold reservoir, we use the ideal gas law to slide along the isotherms, and the relation TV to the gamma minus 1 equals constant to cross the adiabatic boundaries. Plugging in our 513 Kelvin hot state and 323 Kelvin cold state gives us the pressures and volumes for points C and D. A Carnot cycle is a self-consistent loop of state variables. By defining the starting pressure and volume alongside the temperature of your reservoirs, the adiabatic relations mathematically constrain every other point in the cycle. Entropy is calculated by integrating dq over T. In problem 2.8, we find the entropy change of the universe by calculating the heat transfer when freezing water is placed in direct contact with a boiling heat bath. This bar chart tracks the total entropy change for that process. The value drops as we increase the number of intermediate heating steps. Plunging water directly into a boiling bath generates an entropy value of 0.05 C. Stepping it through 4 separate temperature baths reduces that value to 0.0121 C. For problem 2.18, we establish Maxwell's relations by writing exact differentials for the 4 potentials. First is internal energy, then Helmholtz free energy, followed by enthalpy and Gibbs free energy. Because these are state functions, they contain exact differentials. By applying the exactness condition to the Helmholtz free energy, we show that the partial derivative of entropy with respect to volume at constant temperature equals the partial derivative of pressure with respect to temperature at constant volume. These relations allow you to substitute difficult-to-measure entropy values with measurable data like pressure, temperature, and volume. Chapter 3 transitions from fluid equations to combinatorics. Problems 3.8 and 3.21 require counting permutations to determine the odds of dealing specific hands of cards or arranging the letters in the word minimum. Problem 3.13 asks for the winning odds in a repeating three-person coin toss game. Because the sequence repeats indefinitely, we structure Alice's Whiz's probability as an infinite geometric series. Summing this series gives us the result of 4/7. For continuous variables, like the resistor manufacturing in problem 3.14, we rely on the Gaussian distribution. This curve highlights the area within one standard deviation of the mean, which captures 68% of all outcomes. If your data is discrete, like the set in problem 3.15, calculate the weighted average by multiplying each value by its probability, then use those results to find the overall variance and standard deviation. Statistical mechanics connects individual random events to bulk properties. By calculating the probabilities of discrete microstates, we arrive at the same predictable results seen in large-scale thermodynamic systems. Here is your completed roadmap: every boxed derivation, efficiency calculation, and statistical sum for the first 3 chapters. When you sit down for the exam, rely on your established habits. Convert your units to Kelvin, define your expansion path on a PV diagram, and verify your boundary conditions before integrating. If any of these derivations move too quickly, scrub back through the timeline and work through the algebra alongside the visual roadmap. Mastering the specific mathematical requirements of these 25 problems provides the tools necessary to solve the variations presented on the final exam. Good luck.